Hello, this is Dr. Hassan with Innovate, and this is lecture number 52, Analysis of Synchronous Sequential Networks by Signal Tracing, of Chapter 8, Analysis of Synchronous Sequential Networks, of the course Digital Logic Design, Digital Systems, or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in digital logic design, however there are many books available on the subject. Today we will talk about analysis of sequential network by signal tracing, highlighted in red, after we cover the models of synchronous sequential networks, and also we talked about the best model to consider. We talked about analysis of synchronous sequential network using state graphs or state tables. 2 lectures left in this chapter, analysis of synchronous sequential network by deriving the state graph, and VHDL design 7. The procedure of the analysis of synchronous sequential networks by signal tracing is as follows. 1. We assume an initial state of the flip-flop resets to 0 unless otherwise specified. We assume the input changes between clock pulses. And for the first bit, in the given input sequence, we determine the network outputs and the flip-flop inputs. We apply the clock pulse to the flip-flops and determine the network set of flip-flop states. In 6, we determine the outputs, which corresponds to the new states. 7, we repeat step 2, 3, and 4 for each following bit in the given input sequence. To carry out the analysis, construct a timing diagram chart which shows the relationship among clock pulses, the input sequence, flip-flop states, and the output sequence. As an example, we'll take a Mealy sequential network, and we would like to analyze this network based on a given input sequence x equals to 101. We would like to find the timing diagram for this Mealy network. This network is Mealy because Z is X dependent. It is dependent on the input X. So Z is A exclusive or X, and JA is A or X. KA is X prime or X or not X. Okay, so we know all the values from the network of the excitations for the flip-flop A and the output Z. Now we can analyze the network as follows. According to the guidelines, the input is assumed to change between clock pulses, and the initial state for the flip-flop A is equals to 0. So A initially is 0, and as you can see, we cannot time X to be precisely at the edge of the clock, so it will change between the clock pulses. This is the first clock, the second clock pulse, and the third clock pulse. Now, the input X is 101, as specified in the given problem. We would like to determine the value of A, okay, and Z. A changes only at the edge of the clock, since this flip-flop is negative edge triggered, so it will change at the trailing edge of the clock. So A, which is the output of the flip-flop A, will change at the edge of the clock. Now let's look at the input X. When the input X is 1, A is 0, the output Z is 1 exclusive or 0, which is X exclusive or A, okay, which is equal to 1. So initially Z was 1. Now Z depends also on X, remember, because this is a Mealy network, right? A Mealy network. So we know that JA is equal X or A, which is 1, and KA is equals to 0, so we are in the set mode. Hence, upon the falling edge of the clock pulse, the state A will change to 1. Initially it was 0, so it will change to 1. Initially we are in state 0, right? So it will change to 1 at the edge of the clock. Now this will force Z to change to 0 accordingly. Why? Once an A is 0, we know that Z is A exclusive or exclusive OR X. So we have 1 exclusive OR 1 is equals to 0 because X is still 1, okay, and A became 1. So clearly in this interval between the edge of the clock and between the termination, the edge of X, this clock, the output Z will be 0. And this is the glitch. This is a false output. This is a false output occurred because Z dependent not only on A, it depends also on X, because 1 exclusive OR 1 is 0. So Z will change this to 0 accordingly. I hope this is very clear. So with this, when X is 0, now X is 0, so X change value to 0 between the two pulses. When X is 0, A is 1 and A is 1. Z also accordingly will be 1 because 1 exclusive OR X, 1 exclusive OR 0 is 1. JA is 1 and KA, which is the complement of X, also 1. Therefore, upon the negative edge, the second state A toggles to 0. This is the toggle state when A. So initially A, it was 1. A will toggle to 0. A will toggle to 0. And Z will change this to 0 because 0 exclusive OR 0 is 0. And Z will change this to 0. Okay. When X is 1 again, and A is 0, and Z will be 1, JA will be 1, KA will be 0, hence the state A changes back to 1 upon the negative edge. C changes back to 1 about the negative edge of the clock. And the timing diagram for Z is the exclusive OR, or the binary addition for the timing diagram of A and X, as shown. If you'd like to verify this, it's true. From the timing diagram without thinking, we can really just find the timing diagram of Z by taking the exclusive OR between X and A, and you will find the same results. So clearly we get actually two glitches occurred, two false output or two glitches. So for the input X101, A initially 0, then 101, 0, 101, and Z is 1 initially, then give me a false 0, then 1, then a false 0, then 1. So this will be the full analysis of the network, the full analysis of the Mealy sequential network. And we get two glitches here by tracing the signal, okay? And this is it's really a very easy approach to take the exclusive OR. In this case, this is a special case because Z is A exclusive OR X, and you get Z, the output shown here. A second example on signal tracing, we will consider the more sequential network shown. Now, Z is AB in this network, so it does not depend on X, right? JB is equal to the value of X and KB X prime. However, JA is X and B, and KA is given to be 1. So to analyze a mole network using the input sequence X1011, this is given in the problem. We would like to find the timing diagram based on the input 1011. So we have the input 1011, changes between the states as you see. And we assume that the input changes between the clock pulses and the initial state A equals to B equals to 0. Since Z is a function of the state A and B, in this case Z is equals A and B, the initial value of the output Z will be 0. Okay, so Z initially will be 0. Okay, and the output will change only when the flip-flop state changes. When the flip-flop state changes. So, to determine this, the changes according the excitation equations of each of these flip-flop, we know JA, we know KA. KA is constant at 1. We know JB and KB when X is 1. And the state will change to A is equals to 0. And B will be equals to 1. Based on the values, so we have JB is 1 and KB is 0. This is the set state, okay, and B is equals to 1. JA is 0 and KA is 1. This is a reset state, and A is equals to 0. Therefore, Z remains 0 because Z is A and B, which is equals to 0. 0 and 1 is 0. Okay? Now, X changes to 0. X changes to 0. The next bit in X is 0. Also, we evaluate JA and KA, JB and KB, and the state will change to A is 0 and B is 0. Now those both of them, we are in the reset mode, both of flip-flop, because JA is 0 and KA is 1, JB is 0 and KB is 1. Now, if you forget the mode of the flip-flop, of the JK flip-flop, use the next state equation, or we called it the characteristic equation, namely Q plus is equal to JA Q prime or KA prime Q. So Q plus is equal to J Q prime or K prime Q. Okay. So if you use this equation, the general equation, you can find the next state easily as well. Okay. So when X is 0, we found out that Z will remain 0. Then X became 1. Then X became 1. JA will be 0, KA 1, JB 1, KB 0. And the state will change A to 0 and B to 1 after the third clock pulse. Therefore, Z will remain 0, Z which is A, and B which is equal to 0. Then with X is 1 again, so we tested X1, 0, then 1 again, the input. With X1, JA is 0, KA is 1, JB is 1, KB is 0, and the state will change A to 0 and B to 1 after the third clock pulse. Therefore, Z will be still 0. Then X is 1, JA will be 1, so and KA is 1, so this is the toggle mode. JB is 1 and KB is 0, and the state will change A to 1 and B to 1 after the fourth clock pulse. Therefore, Z will change to 1 because Z is AB, and 1 and 1 will be equal to 1. The input state and the output sequences are plotted here. So for 1, 0, 1, 1, A will be 0, 0, 0, 0, 1, B will be 0, 1, 0, 1, 1, and Z will be initially 0, then 0, 0, 0, then change to 1. If the initial 0 of the output is ignored, the output sequence of the Moore machine will be 0, 0, 0, 1, when its input sequence 1, 0, 1, 1. Therefore, for the Moore sequential network, the output sequence is displaced in time delayed by 1 clock pulse with respect to the input sequence. Very interesting. So the Z is displaced by 1 clock pulse, and also from the diagram we can verify that Z is A and is displaced by 1 clock cycle. So Z, if you look here, initially is 0. Initially is 0. Okay. So if you look 0 and 0, 0, 0 and 1, 0, 0 and 0, 0, 0 and 1 is 0. And when flipped to 1, when A initially flipped to 1 and B is 1, Z will change back to 1. And you can see that also from the timing diagram, we can verify that Z indeed is equals to AB, A and B from the timing diagram. Now, this is the most sequential network. Now, again, we proved that the most sequential network does not generate any glitches or false outputs, and it is a good choice, a good designer choice, or the best designer choice, especially when we deal with very high frequency applications. This is the end of the lecture. I would like to thank you so much for listening. Please subscribe by clicking on the blue circle. Hopefully to see you soon in the next lecture. Sincerely, Dr. Hassan.